let's start. Actually, the original plan was that I will finish the presentation from last time, and Chaim will start teaching you the CUDA part. Apparently, we changed it a little bit, and I will cover more basic things about CUDA. So most likely, we'll have one session that will be about 1 hour, 10 minutes or something like that, and then we'll take a break and Chaim will continue for the other part because he wants to discussion all the setup and all the other things for the project, etc. And he is not sure if he will have enough time to cover the CUDA. So I want at least to give you some notions so you could take either book or there are plenty of courses that go on the basics. I don't think that the language itself should be the issue. So we'll start a little bit to rehash about GPU versus CPU, but more than that, I'll cover the very basic principle of CUDA and how it translates to the hardware part. Then I'll move to Nvidia Volta, which is the new architecture which is supposed to directly support neural network, and we'll discuss what are the new things that they put there. And if we have enough time, I'll discuss AMD VEGA. You may think that it is coincident and the names are so close to each other. I assume it is not a coincidence, but AMD VEGA is the architecture of AMD for graphics and machine learning, and they also put special hardware for machine learning. And if time permits, we'll discuss a little bit about research, but most likely I will keep this part for next time. By the way, next time we'll focus mainly on the inference part, and you'll see that unlike 90%, I think, that of the machine who are doing the learning part, that today most of the people are using kind of GPUs or multi-processors. For the inference part, there are a lot of the trend is to go to where ASICs, FPGAs, and not to use GPUs and this part, because it was proven that you can achieve high enough result or high enough predicted results with much lower power and using less expensive devices and expensive in terms of compute power and power, etc. So next time I'll discuss this special purpose hardware for inference. This time we continue to focus on the GPUs because this is what people are doing now. So GPUs, as we discussed last time, so the main point here that we need to remember is that why GPUs are different from CPUs, and because they present a new sort of hardware interfaces. This is the main point that we need to understand all the time. It's not that CPUs are not good, it is not that GPUs are better, they just choose a different design point. And when you choose different design point, so you get totally different results. We'll see it in the inference as well. It is another good example that people change the needle to a different point. By the way, in many senses, Nvidia made some strategic mistakes that they couldn't anticipate it, but actually they persuaded all the world that the main application for GPUs is machine learning, and then they find out that in inference, FPGAs and ASICs are more efficient than GPUs. The only problem is that most of the money are in the inference and in the and not in the learning. So right now it looks like that they have some problems, and it will be interesting to see how they will react to this trend. So we discussed the GPU and GPU's throughput-oriented design, which means that you don't care about low latency. You can have the same, the CPUs just didn't include any feature that try to shorten the access time to the memory or the latency. They don't care about single thread performance. What they care is to get enough throughput, which is the maximum parallelism and the maximum utilization of the entire system. So the design point is different, and I gave an example about the designing of L1 cache. In Intel architecture, it consumes a lot of power because you do everything in parallel. You take all the tags in parallel. You access the cache memory even before you access the virtual address, and actually you access the memory even before you know what is the physical address, although the L1 is physically tagged. So you are not waiting to the TLB, you are doing the TLB in parallel. That actually put a lot of pressure to do the TLB as fast as possible, so you consume a lot of power on the TLB part, on the cache part, and all this effort is in order to be able to access the memory in 3 to 4 cycles, and otherwise it will take you 4 to 5 cycles. So you put a lot of effort in order to reduce the access time to the L1. In GPU, you don't care. You achieve it by having a lot of threads and interchange between them, and you use other techniques in order to get the utilization, and you don't care about the single thread performance. So what's happened if you put an application that needs fast access to the memory, or if you don't have enough parallelism, if you try to run it on a GPU, you get lousy performance. So it is not that a GPU can actually do everything and they are better than CPU. It depends on the kind of application that you're trying to run. And this is the reason that right now people are talking about heterogeneous system. So you have both CPUs and GPUs and FPGA and DSP. For example, in our cellular devices, if you take the chipset or the board of Qualcomm, so you have the DSPs, you have GPUs, you have CPUs, and you have different other special purpose hardware to accelerate different operations. And each one of them is fixed to accelerate different type of computations. There is a research point that if you can actually execute some problem both on the CPU and on the GPU and on the FPGA and on the DSP, what is the best policy and so on, but this is a different topic that this is a research point, a problem we will not access to. We will not discuss it right now. So we talk about the quantitative comparison. I'll skip it, and I'll skip this one as well, the differences. And this is the first slide that shows about the very, very different approach from CPUs to GPUs, and this is the way that you handle memory. And in the GPU, actually, you don't have the notion of register. Register for them is just a physical address space that you can access it in a very fast way. So if you compare it to CPUs, it is relatively slow because maybe it is the GPUs are running in the best case in a 2 gig. But as we said, they are getting the performance for the parallelism and not from the frequency, etc. But the point here that you can decide in a flexible way how many registers you need. You don't have a fixed number of registers which are part of the ISA. You can decide how many registers you need, and then this is a compiled parameter. By the way, all the GPUs, mainly because of this reason, but for other reasons, when you create a code, you never create a code for a GPU. You create an intermediate code, DLX, and this one is translated on the fly by jigging or other techniques to the actual assembly of the part that you are using.
This is a virtual data that the insert added in the last few generations.
No, the GPU from the very basic, they decided that they will work from the user point of view. The assembly is intermediate representation. It's not the real assembly. If you look at it like Intel never exposed the UX.
Yes.
So the actual assembly is the UX, but for you it's x86. So there is something similar, but the IR is a higher level. And for example, there are many instructions that are just inserting, and people just guess that this is the situation. For example, if you want to make sure that if you do something in parallel, there are many places that you have implicit synchronization point, and then usually the compiler just inserts special instructions when it translates the code. And again, this is software hardware interfaces. But the fact that you have a pool of memory and you can divide it into register, local memory, etc., this is a flexibility that we don't have in the regular CPUs. So we talk also about the memory hierarchy, and the memory hierarchy will assume that first of all, GPUs today knows how to handle mainly arrays, and it can be a vector which is one-dimensional, two-dimensional, and three-dimensional arrays. This is what they know, the GPUs, this is what they deal with. You need actually to break the system into blocks, and the meaning of breaking it into blocks is that there is no communication between blocks whatsoever.
Block is you break the memory into blocks?
Yeah, you just have a matrix, and then you said, this matrix, I'll show you an example in a minute. So you say, okay, in this matrix, I will divide the number of rows that you give into 16, for example, so, and the number of columns to 8. And now each one of the blocks is the size divided by 6 or divided by 8. We'll show an example in a minute. The fact that they are independent, the blocks, you can communicate only by a very specific synchronization primitive, but usually you are not communicating between the blocks, gives the system a lot of flexibility when you actually move to a scheduling. Because now a scheduler has the right to assign the block to any of the semi-processors that exist in the system. Once you assign it to the semi-processor, you cannot move it anymore, because the meaning of assigning it to the system, to the semi-processor, meaning that you are taking part of the resource. So you can actually do some resource, you can move the thing around, and there are few academic work that show how to do it, but it is quite expensive. But you can do it because if there is no communication between the different blocks, so you don't need to support coherency. If you don't need to support coherency, you save much of the complexity of the buses. And also, just read, you have if you assume that you have a stream of operations, so you don't care exactly where you assign things, because you assume that you have many of them, and then you can just distribute the blocks according to how many you have in each one of them, and it gives you a lot of flexibility to load balance the system. Yeah.
Okay. 2 questions. If you said that you don't have relation between the blocks, but I have a filter that is working on the edge of the block, so how you get the data from the other block?
You cannot get directly.
This is part of the synchronization?
Yeah, this is part of the synchronization, and there are techniques that you are overlapping some of the areas. the edges, you need to overlap them, but then you know what is the result from the other block only after the synchronization. So what's happened is that you write it to, you have an input and you have an output aerospace usually, and in the input you know that nobody writes it because all the writes are to another block, and then you switch it. So with some overlapping and some tricks in the design, you can actually do the overlapping of the edges. It is not simple and you pay for it. This is the reason that you don't like to have blocks which are too small. On the other hand, if you have some blocks which are larger, so you consume resources, so you have less parallelism, this is part of the problem, how to manipulate your system. You said that you have another question?
Yeah, you assign the block to string processor or a string multiprocessor?
No, so actually, sorry. The system assigned it to string processor, it doesn't matter. Usually in each one of them you have two of them, but in most of the cases it doesn't matter where you put it. There are some resources which are shared between these two, but usually it doesn't matter from the system point of view. From the system point of view, you assign it to string processor, and the internal architecture, what is string, how much you share, it also depends on the different architectures. So you don't like to rely on it. You want to keep things simple and fast. And this is the main topic. Okay, so let's look. So this is in general the GPU memory hierarchy. And in the GPU memory hierarchy, so we have this context that we said that this is the register and the scratchpad, and then we have some short local storage or L1, and we will not refer to the textual cache, which is read only, and then we have the L2, which is shared by everybody. So why you need the L2 if the all the operations are independent? The real effect of L2, there are some effects, but the real effect is to allow you to have some synchronization between the blocks. And since this is in the L2, so actually you can do the inter-block communication quite fast. In the past, you had to do it through the CPU. So in the past, when you want to synchronize between blocks, so actually you had to write a command to the CPU and now the CPU to synchronize the foundry. It is much, much too slow, and then they just move to special synchronization between blocks, and you put it, the best way to implement it is a part of the L2. So this is the reason that in GPUs the L2 is very small. You expect in Intel the L2 is about an order of magnitude larger than the L1. Here it is the opposite. Here the L2 is much smaller because you use it mainly for very dedicated things. So if we look on the hierarchy in more detail, so this is the CPU, and we have textual memory, we have constant memory, and by the way, the textual and the constant are mainly because of the graphic part, and these are read only from the CPU, from the GPU part, which means that the CPU, from the GPU point of view, the CPU can read and write these areas, but the GPU can only read these areas. So usually you are not using these areas, but the texture has also some special structure. I will not refer to it. So if you need, for example, to read a tile, the texture is organized as a tile-oriented. So if you just read a tile, so usually you can do it in one cycle, and if you just do it in a regular memory, so you start having conflict between banks and so on. So because usually in graphics you refer to tiles, so this one is optimized, and when you read the tile you will not have any bank conflict and so on. So if you have a data which is read only, So you want to use sometimes the texture or the concept because it gives you another bandwidth to the internal structure, but otherwise we are not using this one. By the way, if the system, the compiler, do use this constant area to put constants, but again, only if it is read-only. And then we have the global memory. The global memory is GDDR. GDDR is special RAM, which is usually more expensive than DRAM because they need the bandwidth. And also, since you don't need to take care about coherency, so you can have many ports, something that you cannot do in CPUs, because CPUs need to take care about coherency and about other issues for the general purpose. They don't care. So usually such devices can have 12 to and sometimes more ports to the memory. So the access to the memory is very fast and done by many ports that can work in parallel. Now, so the CPU can access the global and the constant and the texture. And the CPU, on the other hand, it takes the GPU, sorry, it takes the GPU up to 1,000 cycles to bring something from the global memory to the inside. This is the reason that they start putting also L1 and L2 caches. But what you really use are the two structures, which is for per thread, each thread that runs has its own registers and it has its own local memory. Now, the local memory is bounded. The local memory actually is a stretch pad as well as the registers. So the thread gets some amount of data, and this data actually is translated into a local for the register and the shared memory. The shared memory itself is per block. So you can bring, for example, you have many threads and you want all the threads to work in parallel, so you bring the data to the shared memory, and this shared memory can be accessed by parallel by all the threads that execute right now. But the registers, of course, they are per thread. So there are specific register per thread, and the shared memory is shared by all the block. Now, what's happened in the shared memory is not enough. You have larger. So this is something which is a little bit tricky, because then the system automatically creates something which is called a local memory. And local memory is, by the way, the local memory is per thread. And the local memory are all the register and all the data which is local only to the thread. But since they don't have devices actually to put inside, so the local memory is located on the global memory in practice. So it takes quite a long time to bring it. Not all the time we are aware about it, that some of the per thread data is remotely, and then we see a drop of performance if it has too much data to keep.
What's the local memory? Is on the
For example, if I use, suppose that my system in the compilation decide to use 32 registers. So these 32 registers are per thread. But physically, because of many reasons, I have space to put only 16 of them. So the system knows that 16 of them will be manipulated inside the area which is dedicated for a register. The other 32 will be saved and on the local memory, because you don't have enough space. Okay. Again, the details of the implementation are quite, some of the details are not publicly available, and most of the time, even when you move from one GPU card to another, it is recommended to run a set of mini benchmarks in order to understand the real behavior your system.
Okay, the shared memory, where is the location of the shared memory?
Okay, the shared memory actually, this is a good question because I have an answer here. So, you see, we have the thread and register a per thread local memory that you can define. This per thread local memory, which are the speed of the register and some usually speed of the register, can be either in the cache or in the device. So usually it is on the device, but it can be on the cache if I access it frequently enough, so it will be on the cache. Now, per block is a set of threads that will work, that will be divided automatically to wraps, and these wraps are scheduled. Each block is scheduled to one of the SMs. Now, all it depends on the number of SMs that I have. Depend on the number of blocks which are assigned to the SM. So the shared memory, which is the physical memory, is divided among all of them, and this is the maximum shared memory that you can assign per block. And you have a full, we'll see in the example. In a minute, you have, when you define a variable, you can define if you want this variable to be on a shared area or on the global. And if you say that it is on the shared, so you will put you on the shared, and then it is up to you to copy it from the local to the shared memory. You just do copy instruction, and this is the way that you manipulate what exists in the global and what exists in the shared memory. So, and of course, we have the device, this is the main memory, and per application device global memory, of course, it is located. So this is the picture of the entire hierarchy of the system. So, for example, if I define something as global, so it will be defined here, but if I want to define it that it will be in the shared area, so I say float my variable minus shared minus device, which means I define the variable my var, which is a type of variable, and I ask to allocate it on the shared area on the device. This is the way that I tell the system where to locate my variables. Again, if I put the global, so it will be defined here. By the way, arrays usually are defined automatically here. And if I define array, okay, there are some predefined definition for things, but I will not go deep into all these details. Questions so far? Sorry for doing it fast, so let's going back. So we have in the device we have a grid, which is divided to blocks, and a grid is a group of thread blocks. Thread blocks may be executed on any processor core in any order and asynchronous with other blocks. So I have no notion who will run first or who will run later, concurrent with other blocks on the core, which means that I need, if for example I want to read something to from the device to suppose that I want to do some operation. So the operation will be divided into blocks. Inside the block it will be divided into wraps. So if I want to make sure that the read operation is done by all the threads and by all the blocks, I must put synchronization point. And then there is a synchronization, so the thread, for each thread is doing read, so I grab it into wrap that now 16, by the way, reads are done by half a wrap, so it's 16 threads are doing it in parallel. But all the parallel operations are done in any order or any possible order, I don't know. and I must put a synchronization point after that to say, okay, I'm done with the read. Now, if everybody reaches the synchronization point, so I know that the read operation was done by everybody.
But if you need the data for one process to read data from another process, because everyone is reading for himself and for the other.
No. Suppose that I just want to read, for example, the global memory to the shared memory, or I want to read it from the device. Let's take an example from the global memory to the local memory.
So why need this synchronization?
Because the inside the block, so one thread can access a memory that belongs to another router.
Okay.
So at least inside the block, I must make sure that all the reads inside the block were done, because otherwise I will read data which is not updated.
Yes.
So the question is correct, do I need to do it cross-block, and many times not. Because optimization is on the block boundaries. But even I just want to do read by all the threads that belong to that block, there is a possibility that I will access data that belong to another route. So in this case, if I know that it will never happen, because I'm just using data within the route, so I don't care to put the synchronization. But if I may access data from another route, and this is suppose that I'm doing AI equal to BI plus something, then I must make synchronization because I'm not sure if all the A's are updated. Okay, so this is the general idea. The multi-thread, the CUDA program, there are the blocks. By the way, the blocks are block of threads. Usually, the structure of the data is similar to the structure of the thread, but it is not necessary. We tend to think that, okay, if I work on a rectangular of 8 by 16, so the data will be 8 by 16. But I may, for example, ask each thread to access 4 elements. And if the thread accesses 4 elements, so actually the size of the data may be larger or smaller than the number of threads, and I need to take care about all this. But let's take the simple example. So these blocks are the structure of the multi-threaded and the structure of the data, but the block, so each one of the block, for example, if I have 2 cores per GPU, so core 0 will get this block, the block 1 will get that one. By the way, it can be any order. But if I have 4 cores, so this is the structure, the core 0 will get 0 and 4, etc. Usually this will be the real structure, but we cannot rely usually because for many other reasons the system may find out that some of the cores are more has more work to do than others differently, but this is just an example. So let's take a very simple example, and this will give us a better notion of how it really works. So we just want to add A plus B equals C. You'll see that it looks simple. It can be not so simple. Okay. So simple kernel will look like this one. Global void add in A star B in B star C star. This is a thread. Look. In this definition, we don't have any notion of the block. We don't have any notion of a structure, nothing. And this is good if we just want to add 2 numbers. But what happens if I want to add a vector? So of course I cannot write it in this way. So just for the notion, so add will be executed on the device. How we know? Because it is global void, and the global said it will be executed at the device. So this one needs to be translated into instruction set in the intermediate representation that will run on the device. On the other hand, it will be called from the host. So the host has a full control on what will be executed on the device. Okay. What's happened here? Okay. So now let's look. Now I want to execute it on an array. In this case, it is two-dimensional array. So I have some global, and the global define two matrices, three, A, B, and C. And now it starts to be interesting. We said that any thread works on a single item. I have no clue what is the structure. I have no clue when I write it how many blocks I will have. I have no clue how many threads will be. So, jumping ahead, when I call it, only when I call it, this is the sign of invocation. Only here I tell the system how many blocks I will have and how many threads per block I will have. Only at that point, the system knows about it. Before that, the system doesn't know. Which means I can run math A with some structure and then math A with another structure. Totally legitimate. So how I can write something meaningful if I don't know the structure of the data? The only thing that I need to know at that point is that the system, when it creates, when the system creates the code, automatically for every thread, it adds I will jump ahead a minute. It will add a set of predefined registers that define for the thread in the structure of the thread block. It gives each thread an ID on the x-axis, on the y-axis, and on the z-axis, because it can be a vector 2D or 3D. Of course, if I'm not using the z, it will be 0. So what information I can get? The thread ID, the block ID, and the block dimension, and the grid dimension. So now from these parameters, so I can actually calculate everything. So I will not go into details, but if we assume that this is the block, this is the grid. The grid is divided into blocks, and the blocks is divided into rows. So the index here of this point is calculated related to this point. So this is a 0, 0 for this block. So here, for example, the thread ID, the thread index on X will be 3. And on the Y, so this is on the X, and the thread index on Y will be 2. In reality, when you just translate it to memory, so in the memory actually is stripping down all the data. So actually this part is mapped here. This part is mapped there. This is the way that you span the matrix. So you can actually, what you need to do is to find out what is the location of this point in this thread, and you have the address of the beginning of the array. So then you need to find out where is the location of this one in this structure. So most likely it will be here. How you calculate it? Because you know how many blocks you have. You know how many elements you have per block. And you know at what row you are. So if you are in row 1, because you counted 0, 1, so you know that, this is translated, that this block, that you have this structure, which is the width of the entire grid, plus the first block, plus the offset from the beginning of this point. So I will not go into all the details, but this is the one, by the way, this is part of the complexity of writing the code here, but after you get used to it, it is okay. So int I is the thread index to point x, int j is the thread point y, and now Cij equal the Aij plus Bij, etc.
Block dim is the width and height of the grid.
Okay, so here I cheat a little bit, because in this case we are defining in the header, we are defining the fixed length. Because you see, I say n, so I know what n is. So the compiler can generate it for me.
Okay.
There's another option that I just transfer a pointer. If I just transfer the pointer, so I have no idea whatsoever what is the structure. In this case, I need to use these parameters and to see what is the thread x, etc., and the block dimension, which means how many blocks I have on the x side, and the grid dimension, how many elements I have in data, and I can calculate it quite easily out of it. So just for the simplicity, we put an example that the size is fixed, and then the system is doing the calculation for me. Okay. So how I invoke it? I said there is an instruction that the structure is dim3, and I said that thread per blocks, for example, is 16 by 16, which means that I have 16 thread on X, 16 thread on Y. This is the structure. I said the number of blocks is n, divided by thread per blocks, that's X, and divide by thread per blocks per y. By the way, if you want to be careful, you write it with ceiling or with ceiling, so you get you are not getting fractions. So you define what is the structure that you want to access, and when you invoke, you said, I invoke the function which is add, math add, and I tell you how many blocks I have and how many threads I have, and these structures are defined here by these two variables, or actually structures, not variables, two structures. So the system takes this instruction, translates it, and creates the thread ID, etc., send it to the other side. On the other side, what I'm getting is that simple. No. I want to do the opposite. This is better. So now when I get it, so now I write my code in such a way that calculates only one single point. And this single point is executed by many threading parallel, or what we call routes. So 32 threads like this will be executed parallel. So if I want to read something, for example, we said that in read it is 16, it's a half a route. So I have a 16 operations which are read. And then there is special hardware that will note maybe next time or this time, I don't know when Chaim will go into the details. There is an operation that actually put all these instructions together to one instruction and then say, okay, read me this instruction. So to the memory, you are not issue 16 reads. To the memory, you aggregate it to one read and say, okay, give me that amount of data and I will split it among the threads.
Does the compiler do for you, or you have to write?
No, the compiler is doing it for you.
And about the if, you do the optimizations you mentioned last week?
Yeah, exactly. The point is that the if in CUDA is translated into calculation of a prediction, of a predicate, sorry. So the if for each thread, when you reach it, the if actually tells if it is 0 or 1. If it's 0, I need to execute it. If it's it's 0, I ignore it. If it is 1, I execute it. So, and if all the instructions in the wrap are either 0 or 1, so I do it in one cycle. If I have a diverge, meaning that some of them are 0, some of them in 1, so I will do 2 passes. One pass with 0, one pass with 1, and the compiler will know how to translate it, if it is 1 pass or 2 pass, or the compiler and hardware together. And they are doing it for you. So you write the if, but the way that you execute it actually is without branches.
From code optimization, it's very important to choose the dimensions, so you get...
Yeah. The dimensions are extremely important for many, many reasons. First of all, the dimensions actually determine if you will execute from the shared memory or from the global memory. And usually what you would do is that you will copy things from the main memory to, or the global memory to the shared memory, and in parallel to this copy, so you will execute something else. And then after you finish the copy, so you could actually access this data and do it in a very fast way. This is one way. You can, of course, execute it for the global memory, but it is much slower. Again, you will have an examples, specific examples. I don't like to go into the details because it will take us too long time. And I want to finish this part to allow Chaim to have his part today. Otherwise, you will not be able to continue. And I believe that soon you will get at least a short exercise so you could actually start writing small examples. But the best is to take your existing examples, and you see that in the Nvidia, when you install the package, so they have a lot of small examples to allow you for add and so on, so you can start with existing examples, run them, and learn. The most difficult part is to understand the principle. Then there are a lot of optimization, but then it is not very difficult to grab it. So this is again 16 by 16, and this is the 2D blocks, and these are the thread hierarchy. Okay. Few words about how you transfer memory, and in this case I'm talking about transfer between the host and the device. Host is the CPU, the device is the GPU. This is the terminology here. So we have actually a instruction which is called, first of all we are doing CUDA malloc. And CUDA malloc, we allocate memory. The CPU tells the CUDA to allocate memory on the CUDA side. So all these instructions are running on the CPU, but CUDA malloc tells allocate memory on the GPU side. Actually, what do you do when you allocate memory on the CUDA side? You don't need actually to go to CUDA. You have some representation of the memory on the CPU side, and you just mark that this area is dedicated for CUDA. Later on, when I have instructions specific, so when I transfer the code to the CUDA, it will do the modification and translate to the physical addresses that you need to address. And you need to remember to do CUDA free, because otherwise you will run out of memory very soon. So the CUDA memory transfer, you have an instruction which is called CUDA memory copy, and then you have a destination and a source. Destination can be on the device and the source on the host, or vice versa. And the point is that I need to tell the system if I copy from the host to device, or I copy from the device to the host, or host to host, etc. So if I copy from the host to device, so the destination MD is on the device. Because I copy from the host to the device. And the source is on the host. If I do the opposite, so the destination is on the host, and the source is on the device. So if I do A plus B equals C, so the A, B, and C are on the device, on the GPU. So first of all, I need to copy A and B. Do I need to copy C? No, because C I will produce. So I need to copy A and B, then to do the operation, and after that I need to copy C back to the host. And this is the way that the host gets the outcome of A plus B. So it sounds quite terrible that you need to copy back and forth all the time. And the point is that because of that and because people complain, so right now they have architecture that they call unified shared virtual address space. In this case, you don't need to copy, the system will do it for you. But be aware, because this automatic copying many times is not efficient. Because the system many times doesn't have the knowledge how to do it the correct way. For example, when you, I described here the copy from the CUDA mem copy, but there is another instruction that's called CUDA asynchronous copy. CUDA copy will pause until the copy is done. Asynchronous will start copying, and only when you use the data, so it actually synchronizes. So there are a lot of optimization that you can do if you know how to do it properly. If you just let the system to do by itself, sometimes it works, sometimes it doesn't. So, okay. Question about CUDA. Okay. This is good enough in order to get you some notion what is CUDA, but of course it is not enough in order actually to start to write programs, but we will have at least an entire session about programming CUDA with many more examples later on, after Chaim will teach you how to set the environment so you could run it yourself. What I would like to do quite fast right now is to go at least in the Nvidia. I'm not sure that we'll have maybe 1 minute on AMD, but the most common GPU today for calculation in general is Nvidia. So I want to talk about very specific area, which is what Nvidia is doing for AI, which is the acceleration of AI. AI is the, or CNN is the main topic of this course. So the first GPU that they announced that it is for machine learning was called DGX1, and this is a very nice machine. The academic price after a huge reduction is $150K. So if you have some spare money and you want to replace your laptop with something useful, so you can spend $150K and get it. So this creature actually has nothing to do with a specific thing for AI, but it is called AI machine. And the reason is that in AI, we are not, most of the time, we are not limited by the compute power. Usually we are limited by the transfer time and by the memory transfer. So what they did, they actually defined a new structure before it was, all the communication was done over the PCI Express, they changed it with something new, which is called NVLink, and the NVLink is much faster than PCI Express. By the way, the next generation of PCI Express will be on the same speed because everybody is copied from everybody. But at that point, the NVLink is much faster than PCI Express. So, and they are using hybrid cube mesh on the device. So all the transfer of data between the cores and between the memories and between the CPU to GPU, they improve mainly the communication part, and this gives them a huge benefit when they calculate a machine learning type of operation. It allows them for picture to actually to be able to bring in from disk or whatsoever. Instead, but also if you have huge data and you want to transfer it between the CPU and the GPU and vice versa, it gives you more bandwidth. It also allows them to move things from the main memory on the GPU to the execution unit very, very fast. They have a small SSD cache of 7 terabyte, which is unbelievable in terms of GPUs. And this is quite fast. So the most innovative part in this device was to improve dramatically the memory transfer.
Was there ID? What ID?
Oh, the Infinity. The communication is
Between the boxes or
yeah,
in
between the boxes. So they have actually they improved the NVLink, but on here also you have the communication between the host, the device, and between hosts. So usually you assume that you have, for example, in a data center, you have many machines which are connected with InfiniBand. By the way, they made a lot of work together with Mendelson and the InfiniBand in order to incorporate our RDMA and the memory movement, asynchronous memory movement. They incorporate them together in part of the new organization of the virtual shared hardware space. Actually look on all the memory of all the CPUs and GPUs as one unit, and then they use both the NVLink but also the quad InfiniBand. So it is either that or this. So either 10 gigabytes or 100 gigabytes communication between the boxes in order to allow you to get a very fast communication between in a data center configuration. So this is easily 3200 watts. I assume that it doesn't work without fan. So this is a huge creature, costs a lot, but it can give you 170 teraflops overall in theory. So recently they announced the Volta. Volta is a totally new architecture, and Volta is not just improving the communication. Volta also include a few very interesting features. So, first of all, they had something which is a mixed precision tensor core. So first of all, they did something which is very typical to Nvidia. They changed the names. So in the past, each one of the cores was called a CUDA core. And now it is totally different. It is called tensor core. So they have both small cores, which is similar to CUDA, a C of a small core with floating point, integer, etc., and tensor cores. Tensor is usually the name used for matrix to vector or matrix to matrix operations. So they want to indicate, yes, we are doing something special for AI. So, higher energy and enhanced performance of L1 data cache. I will not go into all these details, but the basic SN right now has 64 floating point, 32 floating point 32 and 32 double precision floating point, which is not really important, at least not for reference. But anyhow, 3200 watts is not very good for inference in the first place. There also have operations for processing block. Again, I will not go into all the details why 4 instead of 2. It helps them if you have nested loops to do things really in parallel and not to do it sequentially twice. So instead of doing it twice, so now you can execute in parallel all the zeros and the ones in parallel because you have 2 decoders. They found out that sometimes you have nested loops, so you need 4 of them. So you put here a 4 cores for all the structure. But the more interesting part is this tensor core that they have these 2 mysterious structures that if we zoom in, this is what they are targeting. They are targeting special hardware to do 2 things. One is to be able to add 2 matrices 4x4 and to get the outcome in a throughput that on average every cycle you could execute such an instruction. So it is not that it takes you 1 cycle to execute it, but on average, the pipeline is so deep, so actually you could do it, the claim in 1 cycle. And that also allows you to, so you can do matrix multiplication and accumulation. So here it is just, it is not A plus B, but you could actually do 2 matrix multiplication plus addition plus float, and the addition can be 16 or 32 floating points. And all this operation, this is the basic operation that you are doing, and for this one, they actually introduce the notion that this is the pipeline, 2 floating points, you multiply them, and by the way, this is the 1 instance, what you are doing in parallel to all the matrix, and then you can add here either a 32 or 16 bit operation, and you get the output is a 32-bit floating point. So this is the heart of the tensor flow basic operation. And this is the heart of many of the convolution operations that we are doing. So this is the reason that it's considered to be a very, very good processor for AI. They have also blocks of information of data that are not really specified, and my assumption is that they will put, or either they already have or in the future, they will put special hardware for relay operation and for other operations which are non-linear. So most likely they will support this operation atomically as well. So I don't know if they are already having there or it will be extended, especially trigonometry support for short FP, and this is something which they already announced. The short FP, this is the 16-bit floating point that we saw, but also 8-bit operations. They do support this tensor on 8-bit operation. It is not supported by the software, but at least the claim that the hardware supports it, so you cannot use it today. But if you look carefully on the definition, so it exists there, and this is something that most likely in the near future we will see it in next CUDA environment.
We discussed this issue about smaller operation. It's good for inference. It's not good for learning.
Yeah, it is good for inference, and they hope that people will use it for inference as well. But there are attempts to do at least part of the learning by this, but this is the reason that it is lag behind. It's not on the critical path right now. So this is the reason that most of the effort is on the regular learning and the packages. And we know that actually soon, right now, they only have several parts. And the several parts are, again, they are much less power, they consume much less power than the previous, the DX2, but it costs only $10,000, which is maybe reasonable, but not for inference. Soon they will announce the desktop part. The desktop part will be used for inference, and most likely the desktop part will also be used for automotive. And in automotive, what they have right now, they have a card which has ARM cores integrated with GPUs. So I assume that the next generation will be a part that will be integrated with this Volta, and this is what they believe that will be used in inference, at least for automotive. So everything is prepared with this part, trimmed down by power and maybe some capabilities, but will be used for inference, at least in areas like automotive. Okay, I'll take 2 minutes just to, okay, this is the NVLink, I'll skip it. Just to mention that there are other solutions. The other solution is totally different, is the VEGA. It's based on the HSA. We discussed the HSA a little bit last time. The idea of the HSA is to allow you actually to move the software stack from system level to much of it to the user level, and allow the core actually to distribute jobs to the GPU, GPU to the CPU, etc. After some setting ups. And they hope that it will be the future. Right now, it looks like that only AMD is using it. The core itself is interesting. I will not go into all the details here, but the idea here is a little bit different than in Nvidia. In Nvidia, you assume that the scheduling and everything is done on the CPU side. The CPU actually works on the GPU. In AMD, they have what they call a command processor. The command processors actually get all the instruction. The command processor issues the DMA or smart DMA to bring the data into local memory, and then it checks that the data is ready, and only after data is ready, so it launches the execution on a very wide vector machine that they have inside. In the past, it was built on VLAW to be even more efficient. I don't know if they still use VLAW or not. But again, the model of the execution is to transfer much of the work to the CPU, to the GPU itself, and not to rely on the CPU part. So, in this case, everything is mapped in the memory mapped I/O to the same virtual address space, but now one GPU can launch a job to be executed on another GPU. So just by using the memory I/O and the AMD MMIO or virtual I/O that they have, so actually they can actually launch jobs from one GPU to another, from GPU to CPU, from CPU to GPU, etc. So it gives the software a very interesting capabilities that you don't have in NVIDIA.
But how you write this code? How you tell the GPU to issue? I mean, the logic when to issue the code to
the memory. There's a map of the virtual address space that goes to the memory mapped I/O. The memory mapped I/O is like a very sophisticated TLB that tells you each one of the physical what device it belongs to, and after you send something on the virtual address space, But the unified and the MMIO, according to the address, know how to map it to the right place. And there is a definition. I will not go into the detail, but the interesting part here is that since AMD are behind, so they release most of this part in the open source. So much of the information, at least for research, it is very interesting because you have much more information and you have much more flexibility to do things that you cannot do on the GPU, because in the GPU they want to keep most of the things secret, and many times we need just to guess what is going on. On the other hand, I spoke with people that work a lot to optimize. To AMD and say, yeah, in theory they are much better. In practice, they are getting less performance than the Nvidia, and it is less mature. But for the research point of view, so this is a great platform that almost everything is open. More than that, leaders usually don't like to release information outside, and AMD as a followers, they wish to have collaboration, so it is relatively easier to get more information from them. So I think that I'll stop here. So by the way, this is again the idea that the host memory, you have the global and the constant memory, which is quite similar to what we saw in Nvidia, but they have the vector operation. Okay, I'll stop here, and questions. Okay, so we'll take a 5 to 10 minutes break because we want Chaim to be able to complete his part. Again, next week we'll extend about special hardware which is built today for many inference, although people are talking about using it for learning as well. Things like TPU of Google and other very interesting architectures that exist in the market today.